Hello, so we're here today to do the first video of mine going through a real life physics problem. Now, just I want to also say I'm wearing sunglasses inside right now. That's because I forgot my regular glasses at a different place. So yeah, and I just see better with glasses. Um, and then I also want to mention that there are AI generated images like this one. That's an AI generated image, if you didn't know. Um, I use them mostly because I like how it can make eye-catching images like this. Importantly, I did not use it to create the um, create the calculations or to do the calculations. I did that all myself. So on to the problem that I'm going to be solving here. So I want to calculate the amount of ice needed for the ice bath method of cooling wort. So when you're home brewing, after the boil, so you've boiled your wort for about an hour, you want to cool it down as fast as possible. Now, normally out here in Canada, I can just sort of use this method actually, basically, but I instead of adding ice, I just shovel snow onto the kettle for however long. Um, but this one I need to figure out. Okay, how much ice do I need? And I also did the calculations to satisfy my own nerdy urges that I have all the time. Um, Keep in mind there's going to be two big assumptions that I'll talk about in the video, and I'll make it very clear, it's within the calculation. So if you skip the calculations, you won't see them necessarily. But I'll make it very clear what assumptions I'm making, and I will ask you, and I'm asking you now, to please write in the comments whether or not you think that they are good assumptions, like, worthy assumptions, or if they are unreasonable. So let's go on. First up, I have this jug. This is the jug I use to place the ice bath, like to make the ice bath and to place the kettle in. Here you can see the kettle in the jug, and as you see here, I just opened up a bag of ice just to demonstrate, oh, here it is, because I didn't have the foresight to take some good pictures while I was doing it. Silly me. Yeah, the next few slides are going to be a bit technical and in depth, and you may want to skip over them if you're more interested in the result of how much ice you need to cool wort from a boil. Otherwise, keep watching and we can get into the nitty gritty stuff together. One of the first constants we need is the specific heat of water, obviously, and that is defined as 4,186 joules per kilogram Celsius. The second value we need is the latent heat of fusion of water, which is 3.33 times 10 to the 5 joules per kilogram. We also need the density of water, which is 1,000 kilograms per meter cubed. Got that from the engineering toolbox. The equations we will use is Q equals C, as in the specific heat, times M, as in mass, times delta T, as in the change in temperature. And this is the heat change of, a body of something while it's not changing phase. Now, we will also need the Q pH, which I just said Q phase, it's phase change, whatever. And that's the mass times the latent heat of whatever. I did drop the plus or minus here because you choose that based on your knowledge of the problem. And we know that this is gain in heat. So heat is going into the system because we are going from ice to water. All of these, except for the ones mentioned from Engineering Toolbox, was found in college physics, Survey and Buell. I'm not sure if I said that right. Page 370 to 340. Now let's go to the variables we already know. The mass of the wort, we don't know. That's a big unknown. We'll have to calculate. Volume of the wort is estimated to be 5 US gallons. You'll see in our results, it was different at times. It wasn't always 5 US gallons. I don't know if there was actually one that was exactly 5 US gallons, actually. We'll see. Starting wort temperature, I just set at 100 degrees Celsius because it was boiling before. Final wort temperature, 30 degrees Celsius, because that's generally low enough that I can then let it sit and sort of gas off the rest of its heat. I guess that's not really the right term, but you get my point. Mass of the ice. This is our target, so we don't actually know this yet. We're figuring this out. I guess we also are figuring this out, but this is what we're interested in. Okay, let's go to the next slide. Okay, so this is our first assumption. Assumption alert slide. The wort is close enough to water that I can treat it as water for the purposes of the calculations. Given that the wort is primarily water, it's like a very sweet water, I made this assumption. Now, that it may not be correct. Well, it isn't correct. But I am assuming that it is not like that its incorrectness is so small that it won't affect the calculations. So if you disagree with that and you know why, or you have some links and some references as to why, please put them in the comments. I'd be so interested to know. And I think it'd be very cool to have some nice engagement. So first, we will figure out the wort's mass. We're going to stick to SI units, so we need to convert it to kilograms. So this I got from the engineering toolbox. Oh yeah, okay, no, that's right. 1 meter cubed equals 264 US gallons. That was from the engineer toolbox. We can rearrange that to make 1 equals 1 meter cubed divided by 264 US gallons. So we can figure out the mass of the wort to be 5 US gallons times 1,000 kilograms divided by meter cubed times meter cubed divided by 264 US gallons. Now you see, this is the density of water. So this is where that assumption comes in. I didn't say that I'm going to use the density of some other liquid, which I guess I could have in this case, because I do have the original gravity measurements of both of those. So I could actually figure it out. But anyways, let's move on. So we can cross out this US gallons, both at top and bottom there, then cross out the meter cubed, and we're left with kilograms as the unit. After working it all out, so 5 US gallons times 1,000 is 5,000. 5,000 divided by 264 came out to about 19 kilograms. It was actually 18.9393 repeating, so I just rounded it up to 19 kilograms. With all that, we can now use equation 2 as laid out in a previous slide as to calculate the heat the wort lost as the specific heat of water. Again, there's that assumption. The mass of the wort, just calculated here, and the temperature change of the wort, which we also defined as going from 100 degrees Celsius to 30 degrees Celsius. Okay, let's move to the next slide. Now we need to figure out sort of the other end of the equation, where the heat is going, which is obviously into the ice. I named this QIG, which it stands for heat the ice's gain, so you get it, the IG. And that is equal to latent heat of fusion of water, right there, times the mass of the ice, which is our unknown, what we're targeting, plus the specific heat of water, the mass of the ice, and the delta T of the ice. Which then I simplify to get this mass of ice out the equation. So we have the latent heat of fusion of water plus the specific heat of water plus the delta T of the ice. Where, because I didn't define this before, I decided to define it down here. The final ice temperature is 30 degrees Celsius and the initial temperature is 0 because it was just being converted from ice into water. So here we go. We are at our next assumption because we're about to do the full final calculation. The assumption is that the system is isolated enough that I can ignore all other heat transfers that may be occurring. Now again, this assumption obviously is incorrect because as you saw from the photos, I did not have any insulation around the tub, and the kettle is exposed completely to the sort of air around, as well as the ice there. So there will be other heat transfers occurring. However, again, same as the previous assumption, I am making this assumption to simplify the calculations, and I am assuming that it won't hurt the result of the calculations, make the result of the calculations so inaccurate that those calculations are unusable. If you disagree with that, again, please go in the comments and let me know. So we're going to put it all together. The heat the ice has gained plus the heat the wort has lost is equal to 0 because it's an isolated system. Now, that means we can rearrange this to be QIG equals negative Q wort lost, like the heat the wort lost. And then we go and we substitute our previous equations that we found in the other slides. For the IG, QIG, we have the mass of the ice multiplied by the bracket, so it's multiplied by everything here. Latent heat fusion of water plus the specific heat of water plus delta T of the ice equals the specific heat of water, mass of the wort, and the delta T of the wort. Again, this specific heat of water is from our first assumption. So now we can solve for the mass of the ice by dividing this part of the equation, the right-hand side of the equation, by everything on the left-hand side except for the mass of the ice. So then we get the specific heat of water, that this is all a negative too, we have a negative sign. Specific heat of water times the mass of the wort times the delta T of the wort all over latent heat of fusion of water plus the specific heat of water the specific heat of water times the delta T of the ice equals, and again this minus sign, 4,186 joules per kilogram Celsius multiplied by 19 kilograms multiplied by 30 degrees Celsius minus 100 degrees Celsius, which that will give us a negative 70 degrees Celsius. So this will change to a positive. On the bottom, we have 3.33 times 10 to the 5th power joules per kilogram plus 4,186 joules per kilogram Celsius times 30 degrees Celsius, because there's a 0 right here as the final temperature. Now we can go and do our unit analysis, and we eliminate the joules because there's joules on the top and bottom, so it can be x'd out. Now we can eliminate the kilograms on the top since they cancel each other out, and we can eliminate the Celsiuses on the top as well since they cancel out, and same with the Celsiuses on the bottom here, And then all we're left with is on the bottom we have a 1/kilogram. And since it's on the bottom, it flips up and it just becomes kilogram. So finally, we get 4,186 times 19 times 70 divided by 3.33 times 10 to the 5th power plus 4,186 times 30 kilograms, which comes to 12.14 blah, 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 blah kilograms, which I just rounded to 12 kilograms. So it's even in an underestimation there, slightly. So, ice prediction. Close enough. This was obviously an AI-generated image there. And it actually generated this text too, but then I had to change it, of course, because it did it wrong. And I gave it the text. So, estimated ice needed is 12 kilograms. Converted to pounds, we get 26.5 pounds. I bought 7 bags of 7 5-pound bags of ice, which comes to obviously 35 pounds, which the AI told me here. See? Ooh. So I then went and in one weekend I brewed 3 different beers, and they did have varying original gravities and varying batch sizes. It was basically a hodgepodge because I was trying to get rid of a bunch of Wort, which I did. And this is actually one of the beers I'm having now, the low alcohol one. Came out to 3% because I used way too much base malt. But that's besides the point. Let's move on. So here we are at the results. I had to really minimize myself here because so you can see all the stuff. But anyways, we have the low alcohol leftovers, which was 5.5 gallons, 35 pounds of ice was taken, and it went to 30 degrees Celsius. Time to cool, I don't seem to have recorded it, so I apologize for that. The fruity leftovers was 5 gallons and took 30 pounds of ice and had a final temperature of 28 degrees Celsius, and it took 40 minutes to cool to that 28. The hoppy leftovers was a 4.5 gallon batch, 25 pounds of ice to cool, and had a final temperature of 30 degrees Celsius, and it took 45 minutes to cool to that. Now I can make myself bigger again because there's room for me. So as you can see, we have a confused person here just staring at a whiteboard that obviously isn't the data we're looking at, but still sort of takes in the moment of, well, why did it not have that? Like, what went differently? So, why was it underestimated? I said the system may not be entirely isolated, and obviously some heat from the ice, or like some heat may have been introduced to the ice that we did not introduce with the Wort, and in that case, we would need more ice. I also said some ice may have been lost, and that's because it sort of dropped out and there was some spilling of ice. Wort might be harder to cool than water. And finally, I just said, share your thoughts in the comments. Which assumptions, if any of my assumptions were wrong? Did I maybe make a bad rounding error? Like maybe I should have rounded up to 12.2 kilograms or something. Or like, maybe I shouldn't have dropped off that 12.14 kilograms, or like where would have the issue arisen, do you think? But yeah, let me know in the comments, and also let me know if you enjoyed this new video format or video style that I've done today. Thank you.